In this video, we'll cover how to factor the difference of two squares. This is when you factor a binomial. It's made of two terms, where both terms can be written as a perfect square. So how do you do this? Well, if you notice that your two terms that you're trying to factor are the difference, there's a minus, and there's two squares. We'll say the first one is a squared and the second one is b squared. It just turns out that a squared minus b squared factors exactly as a plus b times a minus b. Now, how can you tell that this is true? Well, you can tell that this is true by just multiplying out a plus b times a minus b. If you multiply out a plus b times a minus b, you get a squared minus ab plus ab minus b squared. Sure enough, the ab's cancel, and you get a squared minus b squared. So, if we can ever notice that the thing we're trying to factor is two terms that are both squares, and it's the difference of those two squares, we can skip the work and just write the answer. Let's see how this works. In number 34, I have two terms, m squared and 16. Both of these are perfect squares. This one is just m squared, and this one is 4 squared. So I have m squared minus 4 squared. If you ever have anything squared minus a different thing squared, it factors as the sum of the two things times the difference of the two. Notice that this rule about a squared minus b squared worked here for m squared minus 4 squared. It works for any difference of two squares. In number 35, well, this is t squared. And 121 is also a perfect square. If you don't see that it's a perfect square immediately, this trick makes it so fast to factor that it's probably worth it to check on a calculator or to just check in your head, like, how do these numbers work? It turns out that if you take the square root of 121, you get 11. And that means that 11 squared is 121. So t squared minus 121 is exactly t squared minus 11 squared. And here I have the difference of two squares, so it factors. T plus 11 times t minus 11. Let's see how it can be a little more complicated. To make it a little more complicated, this first term is made of a bunch of different squares. Well, like 25 is 5 squared, and y squared is also a perfect square, and 1 is also a perfect square because 1 is 1 squared. Well, I can't use the rule right now, the difference of squares, because it doesn't exactly look like one thing squared minus a second thing squared. So how can I fix this? Well, 5 squared y squared is also 5y squared. So here I actually have the difference of two squares. If you multiplied 5y times 5y, you would get 25y squared. So I can still write this as the difference of two squares. 5y plus 1 and 5y minus 1. Let's look at number 37. 18 is not a perfect square. So when you look at something with two terms and you say, ooh, it's two terms and there's a difference, maybe it's the difference of two squares. That will save me a lot of effort. If they're not perfect squares, well, you can't factor it as the difference of two squares, really. I mean, I guess you could. Like, this is the square root of 18 squared. But this is not pretty, and we're not really gaining a lot if you go this route. Instead, what you should do with this problem is what you should do with every problem that's not quite nice enough to do. Like this feeling where it's like, oh, if only it was a little different, if only it was a little easier, that's your clue that you should try something easier before you try something difficult. Here, you should try the easier method, which is to say, wait, do these have a factor in common? That's the first thing you should try when you're factoring, is to say, oh wait, these have a common factor. Their greatest common factor is 2. So I'll factor out the 2 first. After I factor out the 2, then I see that now my 2 remaining terms are both perfect squares. And this is easy to factor with the difference of 2 squares. 9 is 3 squared. X squared minus 3 squared factors as x plus 3 times x minus 3. All the different types of factoring all have different levels of difficulty, and whenever possible you should try to use the simplest method you can that improves the problem. This 2 that I factored out, I'm just keeping it for the whole problem so that it's still there at the end when I get my final answer. Let's look at 38. 38, well, 81 I recognize. 81 is 9 squared. Well, is x to the 4th a perfect square? Yes, it is. There is something you could multiply by itself to get x to the 4th. That's x squared. So this looks a little crazy, but when I have 2 terms and I have the difference of 2 terms, I should look to see if both terms can be written as perfect squares, because that makes them easy to factor. So it was worth it to think through, oh yeah, x to the 4th is x squared squared. Now it's the difference of 2 squares, so it factors as x squared plus 9 times x squared minus 9. One thing I haven't talked about enough is how do you know when you're done with the problem? Now, in the earlier examples, especially in the earlier examples in this video, there's nothing that you can really do. I mean, what are you going to do with t plus 11? T plus 11 is just done. X minus 3? Like, nothing good is going to happen with x minus 3. But if you're done factoring and you notice that the factors in your answer are still quadratics, like they still have an x squared in them, it's possible that you could keep factoring, that you could do more of the factoring methods that you've learned to get it broken down even further. In this case, x squared minus 9 is the difference of 2 squares. So I'm going to keep the one factor that's already done, and then notice that the second factor is x squared minus 3 squared. So it's a little sneaky, but this problem actually has the difference of squares in it twice, because I can now break up x squared minus 3 squared as x plus 3 times x minus 3. This x squared plus 9, this is the sum of 2 squares. The sum of 2 squares has no special way that it factors. It basically almost always just never factors. Where the difference of 2 squares has this nice formula, and so the difference of 2 squares is something you should be on the lookout for. Now this problem is done being factored. The last thing I want to show you is how to check your work. After you spend a bunch of time factoring, especially if you've worked on a really hard problem, the way that you check factoring is you check factoring by distributing. Or by multiplying. So for example, let's say that you did number 36, and you looked at it and you got the answer, but this is like a high stakes situation. Like maybe you did this problem on a really important test, and you have time left at the end to check your answers. Or maybe you're working on a homework system where it's really stressful just before you click the submit button on your homework, and you want to really make sure your answer is right. The way you check this is take your answer and notice that your answer has a multiplication in it. So do the multiplication and see if it comes out the same as what you started with. So let's check this. 5y plus 1 times 5y minus 1 would be, well, I'll multiply 5y times 5y. That's 25y squared. 5y times negative 1 is negative 5y. 1 times 5y is 5y. And 1 times negative 1 is minus 1. This is supposed to come out to be the original question. If we did our factoring right, these should be equal. It does. The 5y's cancel, so I'm left with 25y squared minus 1, which is exactly what the original question gave us. just to show you that you can always check factoring questions by multiplying, I'm going to check my answer to number 27, which was in a previous video. If you didn't watch that video, then maybe this is not interesting to see. This is the last thing in this video. If you do some factoring and you check, if you do some factoring and you find that 3x squared plus 14x plus 15 equals x plus 3 times 3x plus 5, well, you can check your answer if it's a situation where your answer matters. X times 3x is 3x squared. X times 5 is 5x. 3 times 3x is 9x. And 3 times 5 is 15. So we were a little worried. We were like, I'm not sure if my answer is right. I'm going to check it. And when I checked it by multiplying it out, I got 3x squared plus 14x plus 15, which is exactly what we started with. So whether you're factoring the difference of two squares, or if you're factoring anything else, you can always check your answer by multiplying it out.